So you'll recall from last time that we were talking about ways to build public key encryption schemes out of RSA. We looked at several mechanisms. We looked mostly at things that didn't work, and then we looked at an example of something that is used in practice, this PKCS number 1, but has no direct proof of security. And I promised you that there were, in fact, ways to build provably secure public key encryption schemes out of RSA, or in fact any other one-way permutation. So let me show you an example of one. This is a standardized scheme called RSA-OAEP, where OAEP stands for Optimal Asymmetric Encryption Padding. This is a scheme that is provably not just IND-CPA, so chosen plaintext attack, but actually IND-CCA, meaning if you take the IND-CPA game, where you get an oracle that does encryptions of either the right message or the left message, depending on the value of the challenge bit, we're also provided with an oracle for decryption. So it's a 2-oracle game. One oracle is actually sort of the challenge oracle that does either the encryption of the left message or the right message. And then the additional oracle that you get is decryption. So the decryption oracle always behaves like it's supposed to, meaning if you provide it a ciphertext produced by the public key encryption scheme, it'll just decrypt it. And and effectively what the IND-CCA notion says is that your messages remain private even in the presence of a decryption oracle. So this would be like if I had a server and I was sending public key ciphertext to it, and I could observe the result of it doing decryption, maybe because I returned some message or because I've got some thread on the server system that can see the outputs of decryption. In any case, whatever the attack scenario is, this is saying, the CCA notion is basically saying that messages remain private even if you can send ciphertext to be decrypted. Well, of course, in the proper IND-CCA notion, there are some restrictions, and in particular, when you get your challenge ciphertext, you're not allowed to send that challenge ciphertext to the decryption oracle because, of course, then you'll learn the value of the challenge bit because it will immediately return to you the message that was encrypted, since, after all, it is a valid ciphertext. And this will allow you to immediately determine whether or not the left message M0 or the right message M1 had been encrypted when you ask that pair of messages to the encryption oracle. So this is ruled out. But you're allowed to send anything else that you like to the decryption oracle. And effectively, in order to meet IND-CCA, you need to make it so that the decryption oracle is in some sense useless, like sending messages to the decryption oracle, sending ciphertext strings to the decryption oracle. Anything that's not honestly generated ought to have decryption fail somehow. So this is a rough, I'm not going to actually write down a formal notion of IND-CCA because I believe at this point you should be able to do that yourself. Just take the IND-CPA notion and add another oracle that just performs decryption. And all the usual stuff carries over. One query implies Q query result still holds. All that stuff stays as is. It's just now you get the extra security of being able to say, even if you allow me to see the results of decryptions of ciphertext of my choosing, I still can't tell you whether or not the left message or the right message had been encrypted. All right, so this is a scheme, RSA-OAEP, that provably meets this stronger notion of privacy. And here's how it works. So I do want to be clear before I move on. There is a difference. So if you've been reading papers or if you've heard people talk about IND-CCA secure encryption, I want you to be clear that IND-CPA and IND-CCA are both notions of privacy. CCA is not an authenticity notion. It is a notion of privacy. IND-CPA says plaintext remain private when you're allowed to see the encryption of messages of your choosing. IND-CCA says plaintext remain private even when you're allowed to see the encryption of messages of your choosing, and you can see decryptions of ciphertext of your choosing. So it's not an authenticity notion, it's strictly a privacy notion. That's different than in the symmetric setting where we had this separate auth notion, which essentially said you can't distinguish between the behavior of a decryption oracle and an oracle that always returns bottom or error, right? Anyway, okay, so IND-CCA. How does this RSA-OAEP scheme work? Well, it looks like this. And what you'll notice, I think, if you stare at it for a second, is this structure has some kind of a familiar feel about it. So be staring at it, and we'll come back to that again in a moment. So here's the construction. We know that in order to be able to use the one-way permutation security of RSA, you'll recall from last time, let me spin up here, that, I guess it was here, yeah, that this works. So here it was specifically for RSA. This notion says that for a uniform point in the domain, that if I provide you with that uniform point raised to the E mod n, so if I go forwards through the RSA function given a uniform point, then it's hard to invert. So we want to use that here. We want to try to exploit that here. So what we want is we're going to ultimately define our encryption scheme, RSA-OAEP, called the public key is going to be the modulus n and the exponent e. We're going to have some string that we're going to raise to the E mod n. And to be very clear about this, you'll recall that in the previous lecture on RSA-based public key encryption, I implored you to never ever use raw RSA. Be clear that we are not using raw RSA here. We are using RSA by raising something to the E and taking it mod n, but this is not raw RSA because we're pre-processing the message before we raise it to the E mod n. So I wanted to be clear that this is not going against what I told you last time. So let's say we have two hash functions, G and H, whose behavior we'll describe in a moment. The RSA-OAEP scheme works as follows. You have some message M, whose length is going to be restricted in the way we'll describe. We're going to take M and we're going to pad it with a string of zeros, and in particular L1 is the number of bits of zeros we're going to append to the message M. We're going to concatenate those things together to create this string here, and we're going to bitwise exclusive OR with the output of some kind of a function G. Well, G is taking as input this thing over here. In addition to the all 0 bits, we're also going to pick some number of uniform random bits. So this is going to be our per message randomness. And there are L0 bits of this. So L0 bits of randomness, L1 bits of zeros. We'll take our random bit string and run it forward through G. So G is mapping from L0 bit strings to how many bits? The whole thing at the end is going to have to be raised to the E mod n, which means that, actually, in fact, this shouldn't be n, this should be log n. I'll have to fix that. That should be log n, and this should be log n as well. N, of course, is the number, the modulus. So the number of bits that we can fit in here is going to be at most log of n, the number of bits that are in the modulus. So G is going to map from L0 bits to, once I fix this, log n minus L0 bits. Why? Because if you look over here, I did it correctly up here, the whole thing has to fit in log of n0 bits. So if L0 bits are coming from here, and L1 bits are coming from here, then the length of message that you can have is log n minus L1 minus L0. That's the number of bits of message you can put in. That's going to become a design parameter. If you have a fixed value of n, say n is a 1024 or 2048 bit number, then you'll be able to figure out, based on how many 0 bits you want to append and how many random bits you want to have, how many bits of message you can push. In any case, we've got these random bits. So, of course, if you think about this, every time I'm making an encryption with this, I'm picking per message randomness. So up to the birthday bound, up to like, if this is L0, up to 2 to the L0 over 2 in the exponent. Calls to this, you're going to get distinct random strings here. So that random string goes in through this function G, which turns L0 bits into enough bits to exclusive OR with this wire here. And we're going to model this thing as a random oracle. And you'll recall that the random oracle model is that G is going to be modeled as a publicly available random function that maps from L0 bits up to log n minus L0 bits. And anybody can call it. The encryption scheme can call it. Adversaries can call it. Everybody can call it because it's basically abstracting away the behavior of a hash function. And of course, we think of hash functions as being compressing things, and that indeed is true. But of course, it's easy to take a hash function and turn it into a non-compressing primitive by, for example, just saying on input X, I'm going to take as my first part of my output, like SHA-256 of 1 concat X, and I'll concatenate that string with SHA-256 of 2 concat X, and so on, right? So I can turn a compressing hash function into a non-compressing primitive in an easy way. So we're going to pretend like this is a publicly available random function that rather than compressing is actually expanding. All right, so this set of random bits here almost certainly is going to be something that's new at the input of G because we're picking random bits, and up to the birthday bound we won't get collisions in those bits. So we're sending something new into a publicly available random function. Well, since this is new, if you think about like the lazy sampling table evaluation of this function, it means I'm picking a new row in the table. It's one that hasn't been seen before, which means that the bits on this wire are going to be uniformly random. Well, that of course means that the bits on this wire, whatever they are, get hit with uniformly random bits. So these are going to be uniformly random bits, and that becomes the first part of our input to the RSA function. Is this now random bit string P1? All right. So those random bits come down here, and they go into this XOR. Well, of course, these bits here are all random now. So we've got random bits going into another hash function, which we're going to, again, model as being a random oracle. This time it is actually compressing because it's going from this many bits down to this many bits. So we've got then random bits coming in, and in fact, more random bits than before. So now the birthday paradox, the birthday bound is going to be in log of n minus L0 over 2 up in the exponent. So really a very unlikely event of having a collision at the input to H, which means every input to H up to the birthday bound is going to be producing fresh uniform random bits here, which then we're going to XOR with the bits on this wire, which means then that this piece is going to be uniformly random. So in the end, again, up to the birthday bound, basically in the length of this random bit string here, we end up with random bits here and random bits here. So of course, when we concatenate them together, we get a uniform random bit string. In other words, we're going to get a uniform element of z star n, which is exactly what we need in order to use the one-way permutation property of RSA. You might ask yourself things like, well, how is it that I know that this thing is going to be an element of z star n? Yes, it's an n-bit string, but the elements of z star n, if you'll recall, have to be bit strings that when you look at them as an integer, so as the base 2 encoding of an integer, that integer has to be relatively prime to n, where n is the product of 2 primes p and q. So in other words, the number that this bit string encodes is a uniform bit string. The uniform number that this bit string encodes has to be relatively prime to both p and q. Well, how likely is that? And if you look at it, you'll see it's in fact extremely likely. Because if you happened to produce a string here that yielded a number that was not relatively prime to p and q, well then you know it's p or p times some constant k, or it's q or q times some constant k. But that means you now know you have a string that encodes a number that shares a factor with p or q, which means if I take now this number, if I take the GCD of this number and n, I'll get out something that is either p or q. So what I'm saying is that you can rest assured that this string here will be a uniform element of z star n, because if it wasn't, then this string here would encode a number that would allow you to recover either p or q, which means you could then factor n. So that would then give you a way to break RSA. So it's extremely unlikely for a modulus size of like 1024, 2048, that the string that's here would not in fact be in Z star M. Okay, so that's how encryption works. Do you recognize this structure? Does it look familiar? It should. It's basically a Feistel network. If you go back, if you were to draw this thing in a slightly different way, you basically get something that looks just like a Feistel network with different round functions for the first round and then the second round. So our old friend, the Feistel network from block cipher days, comes back again in the public key setting to help us build an encryption scheme that has good provable security properties. Well, why should this work? Okay, we've already established the fact that this string here is a uniform element of Z star N with overwhelming probability. Hence, seeing the ciphertext produce here, you're not going to be able to invert it, right? Because that's the guarantee that we get from being a one-way permutation, is the fact that if I take a uniform element here and I raise it to the E mod N, then what I get is something that's hard to invert. Moreover, you'll recall that RSA is invertible if you know the trapdoor D. So if somebody produces a ciphertext like this, you can decrypt it by taking the resulting value that you get here and raising it to the D mod M. But the important point for thinking about privacy is that if this is a uniform string, a uniform element of Z star N, then so is this, right? Because this raising to the E mod N is a permutation, right? It's a bijection over Z star N, specifically because RSA is invertible. So if I have a uniform element and I raise it to the E mod N, I get another uniform element because it's a permutation. And so it's in that way that one can argue that the privacy part, IND-CPA part, is there, is because no matter what message I ask here, M0 or M1, what I get with overwhelming probability is a uniform string here, which means the whole ciphertext that comes back is also a uniform element of Z star N. No matter whether this was M0 or M1, I get a uniform element of Z star N. And so you can play the same kind of game we played in previous proofs, where you can ultimately move the challenge bit that determines whether or not M0 or M1 is encrypted. You can move it until after the adversary is done running. So that's why RSA-OAEP gets the ID-CPA security, is the fact that RSA is a permutation, and this method of padding your message M, this method produces a string that is a uniformly random element of Z star N. RSA is a permutation, so you get, as a ciphertext, again, a uniform element, regardless of the bits of M. All right, well, how about the CCA part? Now, I'm getting to ask queries to my decryption oracle. The only thing I'm not allowed to ask it is the challenge ciphertext that I have in my hand. So you'll recall that for one query IND-CPA, I get to query a single pair, M0, M1, to my oracle, and I get back the encryption of M sub B. Of course, I can compute local encryptions myself because I have the public key. Everyone has the public key, but I've got this one challenge ciphertext. That's the only thing I'm not allowed to send to the decryption oracle, because to be honest, if I just send it to the decryption oracle, then I've acted as a wire, right? I've taken the ciphertext and I've just handed it to the decryption oracle, so of course it's going to behave properly. So I'm not allowed to do that, but I can send anything else that I want to the decryption oracle. So what happens if I do that? Well, let's say that I take a string, I take a ciphertext that I've seen. The same argument will apply if I make up a ciphertext whole cloth. But let's just say I take a ciphertext that I've seen, and I look at the bit string that is this ciphertext. So it's an n-bit long, log n bit long string. And let's say that I mess with some bits, I don't know, up in this piece, up in the upper parts of this string. Well, so that means that when I take the ciphertext, let me try to say this another way. Let's say I have a ciphertext and I raise it to the D, right? So if I'm going to decrypt, I take this thing and I raise it to the D mod N, and I get back some string in here. Now let's say the string that I get back inside of here is not P1 but P1 prime. So I've changed some bits here. P2 I leave alone, but P1 prime is not equal to P1. So some bits up top have gotten changed. So what happens? That means when I come up here, and I run through this, almost certainly this is not a value that this random oracle H has seen. I think I said, I don't remember if I said this or not, but G and H are both treated as independent random oracles. If I change any bits of P1 to P1 prime, then I get some input to H, which has almost certainly not been seen by H before. Which means these bits at the output of H are now uniformly random and independent of everything else, which means that, well, what? That means also then that when I XOR these, I have uniform random bits here. Whatever these bits are, this was P2, I get some other value here. I don't care because when I decrypt, I don't actually check this piece, but I do use the fact that these bits are probably almost certainly not the ones that were used to create this ciphertext, which means I have an input to G that is also new, which means these bits are uniformly random, and now I've got this set of bits here that were changed, that was P1 prime, being XORed with bits that are uniformly random coming off of this wire here, which means these bits are uniformly random. And in particular, almost certainly, that string does not hit an L1 bit long string of zeros. So on decryption, that's what I'm going to do, is I'm going to raise the ciphertext to the D mod M. I'll go backwards through, and you can see, because we've got this Feistel-like structure, that it's trivial to go backwards through. And at the end, I'll check whether or not the last L1 bits of the purported plaintext string that I have are all zeros. If they are, then I'll go ahead and take M and send it up to the application layer for processing. If they're not, then I'll raise an error flag. I'll drop a bottom. So that's if you mess with P1. What if you mess with P2? So I leave P1 alone. I've got some P2 prime here. Well, you can repeat the argument. If P2 prime is different from P2, then even, really no matter what this is, you're going to get something here that's not the random bits that were used to create ciphertext. So again, I get a uniform. I get a new input here, which produces a uniform bit string here. And again, it almost certainly that I don't hit these string of all zeros. So this scheme, that's sort of the hand-wavy argument for why this scheme achieves IND-CCA security, is that almost certainly any ciphertext that you pass to the decryption oracle is not going to result in hitting the string of all zeros at the end. This is an old trick, right? This is a trick we've seen before in the symmetric setting. We're just applying it now in the asymmetric setting. So effectively, RSA-OAEP makes the decryption oracle useless, because almost everything that you hand to the oracle is going to have that oracle return bottom, because you're not going to hit the string of all zeros at the end. So you can sort of see, if you're security bound, it's going to have, in the CCA notion, you're going to keep track of the number of encryption queries you make, which of course is just 1, because we have this 1 to Q result. We'll also keep track of the number of decryption oracle queries that are made. So you can see how that parameter L1 is going to factor in. If L1 is very small, then with just a few decryption queries, you probably will hit something. If I have like a 1 bit, if L1 is 1, so I have a 1 bit of 0 at the end here, then, well, you're going to have to do something here. What was I going to say? Oh, if you only have 1 bit of zeros here at the end, then, an expected 2 ciphertexts, you're going to actually hit that 0, and decryption will return something other than bottom. If you make this, 64, then there's a 1 in, 2 to the 64 chance that you're going to hit this, and so on. So L1 becomes a parameter that's going to affect your resilience to decryption queries. I just realized that you're going to have some kind of, you can't just concatenate these two things together, right? Because you need some way to know when you're parsing this thing. Well, I guess you do know, because L1's a fixed number. Never mind. L1's a fixed number, so you know exactly how long the string is, so you know where the message starts. Anyway, so L1's a parameter that's going to affect the chosen ciphertext part of the security for you. The chosen plaintext part of the security is going to be determined by what? By, I guess, the size of this thing, by L0, right? Because this is the number of bits you pick each time you encrypt. This is the per message randomness. So if you only pick 1 bit of randomness here, then you're only going to be able to create expected 2 ciphertexts for the same message and still remain secure. So the size of L0 is going to affect the privacy and sort of the forward direction and the CPA part of it, and then the size of L1 is going to determine the resilience of decryption queries. But I wanted to say a little bit more about this thing in general, this approach. If you think about what's actually happening here, I sort of was talking through this, but I thought maybe looking at this kind of a set diagram perspective might help. What are we actually doing here? Well, the length of M, as I show up here, is log n minus L1 minus L0 bits. That's how many bits you can shove in. So, for example, if n is a 2048-bit number, then this is 2048 minus L1 minus L0. So maybe you steal like 64 bits here, and I don't know, 64 bits here. And so 2048 minus, what is that, 256, is the number of bits of message you can put in. So you still have a fair bit of room. But what has actually happened here? Our encryption scheme has accepted a message M that is of length log n minus L0 minus L1 bits. Let me zoom in a little bit maybe. So this is where our messages live, in this set. These are all the strings of that length. And what we do is we basically take this entire set and we embed it in a larger set. So this set is now of log n just minus L0, no longer minus L1. This is going to be longer. This is a bigger set, obviously, because these strings are longer. And this magenta here, this is, if you were to take every point M that you're allowed to put in your public key encryption scheme and you pad them with zeros, these are all of the strings that will ultimately be used, right? This is the padding by zeros. And what you notice is that because this set is larger, because this set is bigger than this set, we've embedded these padded strings, basically take M and embed it in a larger space, but the padded strings, these M's that are padded by L1 bits of zeros at the end, they're sparse, right? They don't fill this whole set. They're sparse inside of this set. And that's important. In fact, it's necessary for doing any sort of scheme that's going to be secure against chosen ciphertexts. You need it to be the case that the validly padded strings are sparse inside of some larger set. Why? Well, okay, so we've got some validly padded string here. We've padded it, and now you remember to actually encrypt it, we pick some randomness. We pick these random bits here, and any point that's valid, so this point here, can map to any one of these possible ciphertexts. These are strings that are in bit strings of length log m. These are all the possible places that this one point m concat zeros can map to as a result of the different randomness that you can use. Okay, so we need that. Obviously, we need the randomness, because if we want to encrypt the same message twice, we don't want it to land on the same point twice, for all the reasons we've discussed previously. So we need any validly padded string to have some set of possible ciphertexts that it can produce. So that's for the forward direction. Now, what about the CCA part? Well, let's say that you make up something, you pick some ciphertext maybe right here, and this ciphertext obviously belongs to some set, and so when you try to go backwards, if you fall here outside of this magenta set, if I go from here back to here, so I'm here now, if this is outside of the magenta set, then I know that this is not a string that ends in all 0 bits, in L1 bits of all zeros, so I'll reject this. So essentially the only strings that I can actually decrypt are the ones that land inside here, inside this magenta set. So that's what this padding by all zeros is doing, is it's saying, take all the strings that I might have to process and embed them in some larger set in a way that this embedding is sparse. And it's the sparsity that determines your resilience to made-up ciphertext, basically. If you didn't do this, if you didn't map, let's say that the magenta set and this outer blue set were the same size, so I don't put any zeros on there, then really what I have is a mapping from here straight to here, right? And of course, that means then that if I've got no zeros, if I take any string that's in here, then it will automatically go back to here, right? All strings will end up decrypting properly. In fact, if you imagine, if you go back and look at this thing, if I were to get rid of this, then because there's no randomness, I don't check the randomness upon decryption, everything decrypts properly. I mean, I'll get some string here, right? It may be a gibber string, it may be a random string, but I'll get some string here, and because I made this go away, there's nothing to check. So it's important that you do this kind of sparse embedding step in order to have some guarantee, some hope of being able to be resilient against chosen ciphertext queries. This is the same thing if you think about, like, in the symmetric setting. If you think about using a variable input length SPRP as a way to do authenticated encryption, which was in a previous homework problem. If you have a variable input length SPRP, that means you look like a random permutation in both directions, no matter what the length of the plaintext or ciphertext is. Of course, the length of the plaintext and the ciphertext being the same in this case. But because you take your plaintext and you pad it with zeros, now you've done the same thing of saying, okay, I'm taking my message strings and I'm embedding them in a larger space, but my embedding is sparse because it's only a fraction of the strings in the space that are actually going to be valid with respect to decryption. So this trick of embedding a set that you care about into a larger set in a way that's sparse is under the hood what's happening always when you do this kind of padding-based checking upon decryption. Anyway, yeah, so this is just saying what I told you already. So that RSA-OAEP is a standardized thing. It's used in some financial standards. It appears in OpenSSL. It's one of the things that you can call from their high-level API for public key encryption. One of the schemes you can specify is RSA-OAEP. It's a slightly different implementation there because they also allow for effectively associated data, and this, as I've drawn it, does not, but there's a simple way to handle associated data as well. Anyway, RSA-OAEP is important to know because it is one of the standard methods of building a public key encryption scheme out of RSA. But there is another way that is quite often used. It may not be called this. If you look at the library, if you look at a standard, you may not see these kinds of terms, but you can use RSA in a quite generic way to build a public key encryption scheme. In the last lecture, I told you that you never actually use public key encryption to do bulk encryption of data because it would require you, if you're using RSA, for example, it would require you to have a modulus that's big enough that log of the modulus is a number of bits that you can actually fit your plaintext message into. Right? We saw that with OAEP here. We said, well, if my modulus is fixed to be 1024 bits or 2048 bits, that tells me exactly how long this string can be, which of course determines how long this string can be. And that's true in general, right? If the number of bits here is fixed, then that fixes the size of the plaintext string that I can ever shove in here. So if my plaintext string is, the contents of my hard drive, I'm not going to pick a modulus that's that big. In particular because public key operations like modular exponentiation, even though we have fast ways to do this using square and multiply or other variants, is still like 2 orders of magnitude slower than symmetric key operations. So nobody actually does bulk encryption using public key encryption. Even something like RSA-OAEP, you're going to use this for sending things that are short message strings, because you don't want to pay the cost of having to do large modular exponentiations. So how might you actually use something like RSA to build a public key encryption scheme that would handle messages of arbitrary length, like the entire contents of your hard drive? You do it kind of by cheating. You can either look at this as being very clever or think it's kind of cheating. We're going to build our public key encryption scheme as follows. When you ask me to encrypt a message M, so message M is now a string of whatever length, right? Think of this as an element of 0, 1 star. So I'm building a public key encryption scheme that takes an arbitrary length plain text to encrypt. What I do is I first pick a random element from Z star N. This is going to be my per message randomness. And as I said before, you can basically do this step by just picking a random log of n bit string. So let's say the n is 1024 bits. I'll just pick a random 1024 bit string. That's easy to do. And almost certainly this string is an element of z star n, because if it wasn't, then I could factor n. So I pick this random element of z star n. I take that and I raise it to the e mod n, which I can do because I have the public key. And this is going to be a string I'll call w. This is effectively hiding the per message randomness. Why is it hiding it? Well, because RSA is a one-way permutation and R is a uniform element, that means that R is hard to recover if I show you w, right? I'm going forwards through RSA and I show you w. And that means it'll be hard for you to create R yourself without knowing the secret exponent d. It should be hard for you to recover R. Now, maybe you can recover some bits of R, but you can't recover all of R. And that's important, because even if you can recover some bits of R upon seeing W and knowing the public key, if you can't recover all of it, then if I hash R, and in particular, H is going to be a hash function mapping from z star n down to 0, 1 to the k, where k is going to be the key length for some related symmetric key encryption scheme. So think counter mode in this case. So counter mode over AES, this is like 128 bits. K is 128. I'm going to hash R. And if I treat the hash as a random oracle, then I'm picking this thing uniformly at random. And then I'm raising it to the E. Well, that's a permutation. So I get another uniform random element of z star n. And then I hash R, the underlying R, I hash it. And because it's a random string and n is like a 2048-bit number, n is 2048 bits, so therefore R is also represented in 2048 bits. Almost certainly, I do not get a collision with R. That's a giant string. My probability of collision is now 1 in the square root of 2 to the 2048. So a tiny, tiny number. So I hash R to create a key K for my symmetric encryption scheme. And then what I actually do to encrypt the message M is I use, say, counter mode, using that key K that I just created by the per message randomness and the corresponding hashing of that to create the key. Now, I use that key as the key for counter mode, and I just fix the IV to be 0. How do I get away with that? Well, let me jump forward maybe. So what am I going to return? W, which you can think of as kind of like a hint. W is a hint for the decryption side about how to recover the randomness R. Of course, with the randomness R, you can hash. In fact, maybe I'll just show you decryption. I send W and I send C. We'll come back to counter mode and it's fixed IV in a moment. I send W and C. That's my ciphertext that I'm returning. So you can see what I've done is I have turned RSA, which is an asymmetric primitive, into a new public key encryption scheme that can take messages of any length. And the way I do that is by basically, I'm only using RSA to encapsulate information about the key that's being used. And that information needs to be sufficient that on the decryption side, I can recover the key that was used. But really, all the bulk encryption I do using counter mode. So I send W and I send C as my ciphertext. To decrypt, what do? Well, as I said, I get W and C. I take W, I raise it to the D mod n, which, because RSA is a permutation, recovers R. Once I have R, I can hash R to get the key back. And now I can do counter mode decryption of the ciphertext component C. But of course, counter mode decryption is just counter mode, but now running on the ciphertext as opposed to on the message. It gives me a message back, and I return that. That's how decryption works. Okay, so this thing is a correct public key encryption scheme. It now has a domain that's whatever the domain of counter mode is, so effectively strings of any length. Why do we get away with using a fixed IV of 0 here? We get away with it. You have to think about this. Counter mode is secure if the IV is a nonce, right? So you can implement that with a counter, you can implement it with a random number, and here we're fixing it to all zeros. How do I get away with that? Because every time I encrypt a message M, I'm picking fresh randomness. Fresh randomness generates a fresh key because I hash that randomness. So effectively what I'm doing is I'm calling counter mode on a different key each time. Since I'm calling with a different key each time, I don't have to worry about the fact that my IV is repeating, because it isn't actually repeating, right? The IV repeating is only an issue for a fixed key. All right, let me say that again. If you think about the IND CPA security or IND dollar security of counter mode, we said the counter has to be a nonce, which you can implement as a counter or something like that. But in that experiment, the key is fixed for the entire time that the adversary is attacking this game. So we had to worry about IV repetitions within the lifetime of a key. But here, the lifetime of a key is exactly one call. So we can fix the IV to the all zero string safely. Okay, well, of course, I was making some notes here. You don't actually have to use just counter mode here. This was just a concrete example. Any secure symmetric encryption scheme will work as long as, so you could use, for example, CBC mode here. That would work too. And again, you don't have to be careful about making sure that you have a random IV for CBC mode because you're calling it with a new key every time. So any secure symmetric encryption scheme will work here. And this is an example. This is an example of a paradigm that's called a key encapsulation mechanism, data encapsulation mechanism, ChemDem as it's called. This is a ChemDem public key encryption scheme. And we're going to look at this in a lot more detail in the next lecture because we're actually going to formalize what is a key encapsulation mechanism. But roughly speaking, this section here is encapsulating the key. It's encapsulating the key, so the key is K. In particular, this is the encapsulation of the key K. Why? Because to create K, all you need is R. And R is encapsulated inside this RSA encryption. So this is like the key encapsulation mechanism. This is the key produced by the key encapsulation mechanism. And then this is the data encapsulation mechanism. It's sort of an old school name, but this is the data encapsulation, meaning the actual data I want to transmit, I'm going to encapsulate, or encrypt in this case, using the key that is contained in the key encapsulation mechanism. So as I said, in the next lecture, we're going to see chems in a lot more detail. But I wanted to look at, why should this thing work? Why should this thing work? Well, intuitively, it's going to work because let's say that you see this thing. You see a ciphertext produced. And this is going to be, the encryption of either the left message or the right message if you're playing the IND CPA game. Well, so you get to C, W, and C. And the intuition for why this works is if you don't know the key, then you can't really decrypt C, right? If you don't know the key, and this is just using the underlying security of counter mode, is like if you don't know the key, you shouldn't be able to decrypt, right? That's implied by counter mode being IND dollar secure. So how is it you could come to know the key that's used to in order to decrypt the ciphertext? Well, you come to know it by figuring out from W, if I have W, how do I get back to the key? Well, W tells me R. So if I could find R, then of course I could get the key because I can hash. Everybody knows how to hash. But how do I get R from W? Well, I get R from W by inverting RSA, which is supposed to be hard for uniform inputs, and R is a uniform input. So that's the intuition for why this thing should be secure. Counter mode produces good ciphertext as long as you provide a uniformly random key, and we are getting a uniformly random key, at least if we model H as a random oracle, as we talked about for RSA-OAEP. If I treat H as a random oracle, then fresh inputs are give me uniform random strings K. So counter mode is IND $CPA secure if you give it a random key, and the only way that this key does not appear to be random is if somehow I can take W and invert it to get back R. Because then if I can get R, I myself as the attacker can hash R to get the key back, and now I can decrypt counter mode. That's the intuition for why this thing works. Let me talk you through a little bit more detail how this proof goes. So we're going to wave our hands here a little bit, but I wanted to give you some idea of how this goes. We're going to try to argue very quickly that the one-way permutation security of RSA suffices to prove that this scheme here we just described is IND-CPA secure against a single query adversary. And recall that that suffices because we can go from a one query secure scheme to a Q query secure scheme by this generic result in the random oracle model for the hash function H. That's what I want to prove. If RSA is a good one-way permutation, this scheme up here that we just described is IND-CPA secure if the hash function is modeled as a random oracle. So let me, here pictorially is the IND-CPA experiment in the random oracle model. In a previous set of notes that I released, I talked about how you can turn any security notion into a version of it in the random oracle model. It just means that you provide the adversary with a random oracle. In fact, every algorithm in the experiment can call the random oracle because, again, a random oracle is just idealizing a hash function, and hash functions are publicly computable. So this is the IND-CPA notion in the random oracle model. Adversary A, in the normal, just plain IND-CPA, would only get access to this oracle, right? This is an oracle that on input, let me zoom in a bit, on input in M0, M1, this oracle has a challenge bit that's been installed, and what's returned is the encryption of message M sub B. That's the normal IND-CPA experiment. Now we're going to augment that by providing the adversary with an oracle for H. It can ask value Z to this and get back H of Z. And of course, because everyone gets to call the hash function, the random oracle, we also allow the encryption scheme to call it. And in fact, we see that we need that here because the encryption scheme indeed has to call H, right? It calls it on this value R. Okay, so that's IND-CPA in the ROM. So we want to show if we had an adversary that breaks this encryption scheme with a single encryption query in the random oracle model, then we could use that to build an adversary B that could violate the one-way permutation security of RSA. So we're going to build this adversary B. So here's what we're building. This is our one-way permutation adversary B. A one-way permutation adversary for RSA is going to get the public key. So this is the public key here, and an E, it's public key. And remember, it also gets Y, which is X to the E mod N for a uniform random point X. And B wants to return X. That's its job, to invert this RSA function, thereby violating its one-way permutation security. It wants to do that by simulating this experiment for A, which means it's going to need to simulate both the encryption oracle and the random oracle. And the encryption oracle in particular is going to implement the encryption scheme that's just above. So it's the usual kind of thing. We're building a B that can simulate this experiment with the particular encryption scheme up here in this oracle. All right. Well, so to simulate this experiment, of course, the first thing we have to have is a challenge bit. There is no challenge bit in B's native experiment because it just gets this N, E, and Y to produce an X. There's no challenge bit there. So B picks that challenge bit itself. It's going to have to simulate encryptions here. And to simulate encryptions, it's going to need a key for counter mode in particular. But we'll come back to that. But in any case, for right now, it picks the challenge bit B, and it picks a key K, and we'll see why. All right, we know A is going to make a single query to this oracle, right? That's all it gets is one query to the encryption oracle. So we'll talk about that in a minute. It can make many queries to this oracle. This is like saying I can compute lots of local computations of this hash function, lots of them. And so by having a query this oracle, it's like we're basically resource counting. We're trying to account for the number of times that you can locally run a hash function yourself as part of your attack. So A is going to be asking many queries up to here, and we're going to have to respond with something. Well, we know that the behavior of a random oracle is if you provide me with an input that I haven't seen before, I just return a random string here. So that's easy enough to simulate. But we're going to just have a little bit of cleverness here about how we're going to simulate these random strings, because we want to somehow use A to help us invert this RSA instance that we have. We want to use A so that it can tell us what the value X is that's underlying the Y that we've been provided as input. We want to use A to help us invert this right here. Well, okay, so whenever A asks a Z, when A asks a Z, so when A asks an H query, if he asks a Z, what we're going to do is we're going to check if Z raised to the E mod n equals Y, the thing we were handed. Recall, this is what we're handed. If A ever asks a Z, well, we can, of course, it's going to ask these things. When it does, we raise it to the E, which we can, of course, do because we know E and we know N, they're part of the public key. So we take Z, we raise it to the E, take it mod N. If that hits Y, what do we know? Well, we know that, in fact, Z is X, the thing that we need to return, because RSA is a permutation. There is only one value here, Z. There's only one Z that can produce Y, and in particular, it's this value X that we needed to get. So we just check. Whenever A asks us a query, the first thing we do is we take that query, we raise it to the E mod N. If it equals Y, well, then we win, because Z has to be X. We still have to return something. So what are we going to? We're going to return this key that we picked up here. We're going to return this key. And so I'm showing here that we've got some in our implementation of this adversary B. We've got some table we're keeping track of. This is a table for the function H. So at that point Z, we're going to write the key K in there, the one that we picked. We'll see how that key K is going to come in a moment. If Z to the E mod n is not Y, well, then we just are going to return a random string of the appropriate length and not keep track of even what it is. We could write this value into this table, but you know, in the actual proof you would write it in, but really you don't need to, right? You can safely return a uniform random string. Let's see why that's the case. Let's say that A never manages to call H on a Z that passes this check, meaning it never calls it on the value that we need to return. Well, for every one of those, it's received a uniform random element in return. And in particular, when it comes time for it to ask its single encryption query. So when A asks M0, M1, then we're going to do, this is where we're going to embed our RSA instance. We need to return, if you look up here, we need to return a W that is something to the E mod n, where that something was a uniform element of Z star n. Well, what does B get? B gets a Y, which is X to the E mod n, where X is a uniform element of Z star n. So X plays the role of R, Y plays the role of W. So we're going to set W to be equal to the Y that we got. Okay, let's think about that. In that case, the key that we should return should be, well, if we're using Y here, and Y is equal to the X to the E mod n, where X is the thing that we want to recover, what we should return for the key is H on X. But we don't know X, right? We don't know X unless we actually get a Z from A that gives us Y. We don't know X. But that's okay. We're going to pretend like it's okay. We're just going to return this uniform random string. Why is that okay? Because if A never manages to cause us to go into this thing, if it never manages to basically call H on the X we need to return, then the values that come back are uniformly random, and this W is going to be completely independent of the key that's being used here, right? This key is the key K that we pick up here. So it's like on this one query, we're going to use this key K. And if A never manages to call this oracle on X, the point that we need to return, then everything that it gets in response is a uniform random string that is in particular independent of the string K that we use when we create our counter mode ciphertext. So basically it learns nothing about the key K that's used in counter mode unless it queries the random oracle on the point that we need to return. So in effect, the information that's in here is independent of this because this here, the W, is X to the E mod n. This key goes with that X in the sense that you hash X to get it, right? You're supposed to in this scheme. But if I never call, if all I'm ever getting back from this oracle are strings are independent of K, then this thing leaks nothing whatsoever about the actual key that's being used. It's independent of this key. And so as a result, this ciphertext is going to, based on the security properties of counter mode, is going to leak nothing about whether or not M0 or M1 was encrypted. We're encrypting M0 or M1 under a key K, which is independent of this and independent of every value that was ever returned here. So as a result, this is useless, and it all comes down to now trying to break counter mode with a random key K, but we already know counter mode with a random key K, you can't distinguish anything about this bit. We've already established that long ago. So that's the intuition for why this works. If A never calls the random oracle on a value on the value X that we need to return, then it might as well just be simulating this itself locally, because everything that's returned from this is going to be independent of the challenge ciphertext that it gets when it makes its single encryption oracle query. So essentially, this is kind of a clever thing. If A never calls this on the X that we need to return, then this oracle is useless, and the probability that A manages to guess whether or not it was the left message or the right message is encrypted is the same as the probability that it manages to tell whether the output of counter mode is the left message or the right message for a uniformly random key K about which it knows nothing. We already know that that advantage is 0, right? We've already done this iteration. So if the adversary never manages to help us win the game, it can't win its game. Let me say that again. If the adversary never manages to help us win our game, inverting RSA, by calling this random oracle on the right point, if it never manages to help us win our game, then it cannot win its game because the challenge bit is only ever used here in this one encryption. But because counter mode provably hides that challenge bit when you have a uniformly random key K about which the adversary knows nothing, which it knows nothing given that it never called this on a point that helps us, then it can't be that A can guess the challenge bit because counter mode hides it completely. The only way that A manages to get any information that helps it to recover the challenge bit B is if in fact it calls the random oracle on exactly the value that we need. If it does that, then we win and the game is over. And that's basically the argument for why this scheme here, is in fact secure. This is an example of a random oracle model proof, and you basically just need in your proof to argue along these lines that you can always embed. And so essentially what we're using the random oracle here in the proof in our reduction for building B, well, here we're just checking this. We're basically using the random oracle as a way to keep track, right? If it's like it makes a hash query, and we're basically having the random oracle here provides us with a way to say, okay, if we were a fly on the wall, if we were part of the attack that A is producing, and we could see the hash queries that are being made, the only way that A could actually manage to break the challenge ciphertext that it gets is if it actually called the hash function on the inverse of some RSA instance that we could embed. So we're using the properties of the random oracle here. We're not really using it for anything other than like keeping track of what hash values are produced as part of the attack. It's a very simple use of the random oracle model. So that's basically how you prove that this scheme is secure. I would recommend that you go back and listen to the last 10 minutes or so over and get the intuition here for how this works. But it really boils down to that the only way to get any information about the challenge bit B is if you call the random oracle on exactly the value that we need in order to invert. This is a very common trick. We saw the same kind of trick when we were looking at the security of Elgamal encryption under the DDH assumption, right? Remember, we said the adversary for IND-CPA for Elgamal is making a single encryption query, and on that encryption query, we're going to embed our DDH instance in a way that allows us to say, unless you can help us solve this DDA instance, you can't possibly violate the IND-CPA security of Elgamal. Yeah? So we cleverly embedded our DDH instance into the single encryption query that the adversary gets to make. There was a proof that hashed Elgamal is secure under the CDH assumption. And there, this is in the random oracle model for the hash function H. There, we're using the random oracle as basically a way to collect up the queries that are made. And at the end of the game, we check to see if among those queries is one that helps us to win the CDH game. And we argue that if there isn't one in there, then you can't have won the IND-CPA game to start with. We're doing a similar kind of thing here. We're saying on that one encryption query, we're going to embed our RSA instance Y, and then we're going to just use the random oracle as a way to help us. So it's just the same trick over and over again of saying, for the single encryption query that we get for IND-CPA, we're going to embed the instance of whatever it is that we're trying to break, whether it's DDH or CDH or RSA, one-way permutation. We're going to embed our instance in that one encryption query. This is the trick that's used over and over again. The random oracle model just gives us a way to keep track of the queries that are being made and to use the fact that what's returned is a uniform random bit string, and that helps us to argue about all the return values being independent of things that are important in the experiment. So that is an example, two examples now. RSA-OAEP is an example of a standardized RSA-based encryption scheme that achieves IND-CCA security, and we had some discussion of why it does that. But you are length of message that you can send, right? You're limited by the size of the modulus. If you want to build an encryption scheme out of RSA that has effectively an arbitrary sized plain text space, then you do it like this. And this is an example, as I said, of a broader paradigm called the chem-dem paradigm. And in the next lecture, we're going to see in detail, we're going to actually formalize what a chem scheme is, and then to build a public key encryption scheme. And it's going to look very much like this. It's just we're going to kind of generically replace what's happening here with a chem, with the encapsulation part of a chem, and we're going to replace on the receiver side here, this is going to be the decapsulation procedure for the chem piece. Anyway, more on that next time.